Okay, Algebra 2 students, today we are looking at Unit 4. Hopefully you got a good grasp of Unit 3, which was graphing linear equations and all of the little properties and stuff like that, because in all of Unit 4, what we saw was more lines running around inside of our graph at the same time. So clearly we are looking at systems of equations. Now in Unit 4, we found different methods for solving systems of equations. We learned to classify them into their different categories, and then we branched into inequalities in our systems and learned how to draw and shade those. So let's take a look. The first thing we had was systems of equations by the substitution method. Now, the methods that we went over are by far not the only methods to solve systems of equations. So if you have come across additional ones in your travels, those are certainly viable as well, including a couple of methods that the calculator has to offer. But be advised that the substitution and elimination methods that we're getting ready to review, those are kind of typical methods that you're expected to know. So it is entirely possible that problems you may face either on a semester test or possibly an ACT or SAT or some kind of college entrance exam may expect you to be able to demonstrate particular steps of the substitution or elimination methods, even if you know other methods of solving the equations. You may not be able to answer the questions that they're asking unless you master these two methods. Okay, so obviously systems of equations is a situation where you have multiple equations operating in the same graph, which means these two lines, or whatever the type of curves are, they're running around in the graph, and it is entirely possible and probable that they will hit each other at least one location. That means there is at least one ordered pair, x comma y, that will solve either of the equations at that particular location at the same time. That's what we call our intersection. It is the solution to the system. So the first method we looked at was the substitution method, and it is called the substitution method because of its tendency to make you substitute into the equation. So let's look at the step-by-step here. You pick either equation that you want and solve for either variable that you want. So typically you have in your two equations, you have an x and a y in one equation, you have an x and a y in the other equation. Look at those four variables. Typically with the substitution method, one of those variables will appear easier to solve than the other three. Okay, pick on that one and then go through your normal 5 steps for solving an equation and isolate that variable. That's step 1. Once you have that variable isolated, it will say that variable equals, and then you'll have a bunch of junk on the other side of the equation. What we're going to do is we're going to take all that junk and we're going to install it or substitute it into the other equation in place of this variable that you've just solved for. So let's say, for example, you have x equals 3y plus 4. You would go to the other equation, find the x, and take it out, and instead substitute in 3y plus 4. Okay, so that's step 2. Substitute that value into the other equation. When you do this, the equation you just substituted into is going to have a whole bunch of variables in it, but those will be the only variable that are in it. In other words, you will no longer have an x and a y in the problem. You will only have x's or only have y's. If that is the case, then we ought to be able to solve that equation all the way down to where we get the variable equals some number. So like x equals 5 or y equals 2 or something like that. That is step 3. Step 4 is to take this half of the solution that you just discovered back to the original system. Okay, so we're going to substitute the value you just found into the original equation you used in step 1. So the last couple of steps you've been particularly working with one equation. Now we're going back to the original problem and we're working with the other equation. Okay, so substitute your variable's value into the original equation, and that will give you a new equation that once again only has one variable. That variable will be the one that we do not know a value for yet, but after you solve it out, you will have the other value. So in step 3, you are finding a value for either x or y, and in step 5, you are finding the other value for y or x. Okay, when you put those two values together, you have an ordered pair. That is where your system runs into itself. Okay, the rest of this in this lesson is just examples. So please go back and look at the examples if you need that, but it is simply obeying those 5 steps. We spent a couple of days working on that, and then we came back and we looked at the elimination method. Now, the elimination method, a lot of you found it to be easier than the substitution method, but in all truthness, what we have is we have 2 different methods, and those 2 different methods work well for particular types of problems, depending on how it's set up. Okay, so the elimination method actually has more steps, but it does tend to flow a little bit easier as you are working through your problems. Okay, so the elimination method focuses on removing a variable from an equation by combining the 2 equations of the system. Now, in so many words, that's not all that different from what we did with the substitution method, only this time we're not installing one equation into the other. We're actually trying to find a way to cause part of the system to eliminate itself by adding the 2 equations together. Okay, so here's your step-by-step on elimination. Look for a variable that has coefficients in common, but with different signs. For example, maybe you have positive 2x's in one equation and negative 2x's in the other equation. That's what we're looking for. The x's have coefficients that are the same. They are both 2's, and one of them is positive and one of them is negative, so we have different signs. That's what we're looking for with the elimination method. If you already have that in your system, then the problem is set up nicely for elimination, and you get to skip all the way down to step 4. If you do not have that in the problem, all is not lost. It can be set up. Okay, so step 2, what you would do is look at your equations and decide where would be a convenient place to actually have this thing where you can have coefficients in common but with different signs. Now, it's not already in the problem. We established that in step 1, but maybe we can cause it to happen by simply multiplying one of the equations all the way across by some constant. For example, maybe you have positive 1x's in one equation, negative 2x's in the other equation. Hey, one of them's positive and one of them's negative. If we could just get that 1 to become a 2, then we would be good to go. Well, we can make that happen by multiplying that first equation by a 2. Anyway, so on step 2, you're just kind of doing some thinking. You're looking at the problem and trying to decide where can I make these coefficients come out the same value but with different signs, kind of figuring out a number that you might need to multiply by, and then on step 3, you're actually doing this multiplication. So this is going to involve multiplying at least one of the equations by a particular value. Now, if needs be, you can multiply both equations, and you can multiply them by whatever values you see fit. So you don't have to say multiply both of the equations by the exact same value. If you want to multiply one equation by a 9 and the other one by a negative 4, then go right ahead. Okay, but then write out your new equations after this multiplication has been done. Now you kind of go back to the beginning of the list here. If you have done this correctly, then step 1 ought to work now. Look for a variable that has coefficients in common but with different signs. If you did it right, this ought to be there and you can jump to step 4. If it's still not right, then you did something wrong either in your thinking on step 2 or in your multiplication on step 3, and your problem is still not set up for elimination, so try again. Once you finally get it set up right, you get to go to step 4, which is to combine the 2 equations by addition. Okay, so you add the 2 equations together. If step 1 is correct, one of your variables will eliminate itself. For example, positive 2x's and negative 2x's, when you add them together, you now have 0 x's. They will no longer show up in the problem, and you will have a new equation that talks only about y. Okay, so you add the two equations together. This gives you a new third equation. Write it down. You now have a third equation that is only working with one variable. Solve for that variable. Okay, that is step 5. And then step 6, just like with the substitution method, take it back to the original problem and plug it in to either equation. Okay, this should give you yet another equation that only has one variable in it. So in step 5, if you solved for x, in step 6 you're actually now finding y, or vice versa. The rest of this was examples, so be sure to go back and look at those notes if you have problems with that, but it's basically all just following the 5 steps, or 6 steps in the case of elimination, rather. Okay, after we spent about a week working on the substitution and elimination method, we now came back and said, you know what, there are different categorical names for what may be happening to you in your system. So we picked up a little bit of vocabulary here on these days. As we saw, our equations may run into each other. So there is a location, x comma y, that actually works for both of your equations at the same time, at the same place. Okay, now we've been looking at linear equations, but of course our equations can do anything they want. They can bend all over the place, and we saw a good bit of that as we went through the different parent functions through the last half of the year. Okay, but the point being, if there is a location where the graphs exist at the same time at the same place, then this is what we call a consistent system. Consistent means there are solutions. Okay. Another term that we came across was that the possibility that no matter what your graphs are doing, whether they intersect or not, when you graph your two equations, you get two different graphs. Now, that doesn't mean they have to be different styles of graphs. They can absolutely be both lines or both parabolas or both square root functions or whatever. But if you get two different things existing at different places in the graph, then this is what we call independent. Independent means they are not the same graph twice. Okay. Now the flip side of consistent, meaning that there is a solution, is inconsistent, meaning that there is not a solution. This happens in the case of parallel lines or possibly graphs that are opening either at exactly the same speed or possibly opening away from each other. Okay, when you are working to try to find a solution for an inconsistent system, what you will happen is you will end up arriving at some type of a non-true statement. For example, maybe you're going through the substitution method or the elimination method or whatever, and you will end up with a statement that says something like 1 equals 2. Well, obviously 1 does not equal 2. Okay, so you'd want to backtrack a little bit, make sure you haven't made any math mistakes. But once you're sure that you haven't done anything wrong and the problem is simply arriving at a lie, then the message here is the problem is trying to communicate with you. It is telling you that you are looking for something that does not exist and you should stop looking. So if you end up at a false statement, you might possibly be looking at an inconsistent system, trying to find a solution where there's not one. And the last type of system, this doesn't happen too often, but it is one of the categories. Okay, and this is the possibility that maybe you have two different equations that when it comes down to it and you graph it, you actually do not get two different graphs. You get the same graph exactly twice. Okay, and when this happens, there's actually an infinite number of solutions here, and you would be able to identify this as you're working through doing substitution or elimination. Okay, possibly you arrive at a true statement like something like 5 equals 5. Okay, you would want to backtrack and make sure you haven't done anything incorrect, but after you realize that, yeah, I'm doing it all right, I just ended up with some kind of a true statement, x equals x, -9 equals -9, stuff like that. Okay, it is trying to tell you that you are looking for a solution and the solutions are everywhere. That is dependent. So a little bit of vocabulary there. We've mentioned these from time to time throughout the year, and it's pretty clear that most people either never knew them or forgot. So you might want to have a look at these four terms. The rest of the unit was getting into inequalities. So we started off with a little bit of a basic reminder on how inequalities work. Specifically, we looked at inequalities in 2 dimensions. Sorry, we looked at them in 1 dimension, and then we came back toward the end of the unit and looked at them in 2 dimensions. So let's take a look here. Okay, now the concept of something being greater than or less than. Okay, it's a very simple concept, but some of us have made it considerably harder than it needs to be. All you need to remember is that for something to be greater than something else, it simply means it's further towards positive infinity on the number line. And so, conversely, something being less than means it's closer towards negative infinity on the number line. And this is still giving some of you some very basic conceptual problems, because we still want to think that the bigger the number, the bigger the value, and that's not necessarily true, especially when you get on the negative side of the number line. So just remember, if something is supposed to be greater than something else, okay, then on the x-axis we're talking about it being further to the right. If something is greater than on the y-axis, then we're talking about being further up. For less than on the x-axis is further left. Less than on the y-axis is further down. Very simple. Okay, so we talked about that a good bit. We also talked about the different ways that we have of plotting or graphing points. In 1 dimension, it's just a plot, and it's an important concept to remember. We needed it in our graphs as well. Okay, if something is simply greater than or less than, that means the particular value that you're looking at is a boundary. It's not actually included as part of the solution. So when you have to go to a number line or to a graph and plot it in there, okay, we use an open dot to represent that the point is not included. However, if you have something like less than or equal to, greater than or equal to, that means that yes, it still is a boundary just like before, but the point itself is also included as part of the solution. So we close that point in, fill it in to show that it is included. Okay, and then on the shading in 1 dimension, all we did was just shade towards the less than or greater than values according to the problem. Okay, so there were several examples that were worked out inside of there. If you're struggling with it, still give this a look. There was only one real change that you had to look at, one thing to pay attention to in the math, and this was the possibility that you might have to multiply or divide by a negative sign in order to solve for your variable. If ever you find yourself multiplying or dividing the entire problem by a negative sign, that is going to cause the axes of the problem to reverse, which means your less than or your greater than symbol, whichever direction it's pointing, it must point the opposite direction because we multiplied or divided by a negative. Now that is only for multiplication and division, so do not do that if you are adding or subtracting a negative, only if multiplying or dividing. I think the rest of this was examples, and it was. Okay, then we got on to linear inequality. So we're into 2 dimensions. Now, what this guy does is when you have a linear or any type of an inequality for that fact in 2-dimensional space, you are going to have 3 different possibilities as far as solutions are concerned. You have the set of points that exists on your curve, which is what we'd been graphing earlier in the unit by substitution and elimination. Okay, but then we also have the 2-dimensional space that's on one side of the curve, and then the 2-dimensional space that's on the other side of the curve. And with an inequality, one of these 2 areas of 2-dimensional space is also going to contain solutions that will make our inequality true. Okay, so a couple of things to keep in mind here in 2-dimensional space. When it comes time to draw your line, just like with the number line, we need points that are included and points that are not included, like with the open dot and closed dot. Okay, but now since we have a curve, we are looking at a line of some kind. if the line itself is actually going to be included as part of your solution, meaning it is less than or equal to, greater than or equal to, we're going to use a solid filled in line. But if the line is just a boundary and not included, okay, like a less than or a greater than, then when you draw your line in, you will dash it, which represents that this is its location, this is the boundary, but anything that lives on this curve is not actually part of the solution. Then for our shading, just like with the number line, we will shade the direction of the greater than or less than values. Okay, so there's a couple of different ways to go about the greater than or less than shading as far as which direction you want to shade from your curve. One of the ways is if you trust the math that you've done, you can actually read the problem as it is stated. Like this problem that you're looking at now says y is greater than the curve. So you could simply ask yourself, well, there's the curve in the graph. Okay, where are the y values larger than this? Okay, well, y values are larger if you shade upward. That's where the bigger values of y are, so you can shade upward from there. That's one way to go about it. Other way to go about it is to pick a test point. Personally, this is the method that I use. I pick a test point in open space, usually the origin if it is available, because 0, 0 is easy numbers to work with. Okay, and I'm going to plug in this test point that I select into the equation for the x and the y value in the inequality. Okay, so I'm going to take x out, and I'm going to put a 0 in. I'm going to take y out, and I'm going to put a 0 in. That will leave me with two numbers, one on the left and one on the right, and then all I have to do is read the inequality and decide if it's true or not. Okay, so in this particular case of this particular graph, when I plug in 0 and 0, I have a statement that says 0 is greater than 3, and then I just ask myself, is that true? Because if that's true, that means I'm going to shade towards the point that I picked. If it's not true, that means I'm going to shade away from the point that I picked. And in this case, 0 was not greater than 3, so that means the origin did not want to be in the area that was to be shaded, so we would shade the opposite direction from it. And that's pretty much the way that it worked. Got a little bit more complicated, but still the same concept when the problem turned into a system. Okay, still no change as far as coming up with the solution to the system, but now we simply need to worry about the fact that there's not two areas of two-dimensional space in the graph. There are now 4 areas of two-dimensional space, or depending on what kind of a system is, maybe there's only 3 areas of two-dimensional space, but okay, it just depends. We need to worry about where does the shading overlap, not just where does the shading exist. Okay, but you've got 2 graphs, okay, in there, and following the same strategies, either reading the inequality or by plugging in a test point, one equation at a time. What we ought to be able to do is we ought to be able to come up with 2 different directions of shading, like you see at the top of the screen there. Now, some people choose to actually kind of lightly shade their graphs and then look at where the overlap is. Some people draw little arrows pointing away from the particular lines, indicating where the shading is going to want to exist. Whatever works for you works for me, but the key is, the final line is, there is only one area of the graph that exists as far as the shading is concerned in both graphs at the same time. And in this particular case that you're looking at now, the area that they had in common was to the left of the intersection, okay, for the solution. So that is the only area that actually gets shaded. And that's how we graph and shade our systems of inequalities. Okay, so that's pretty much what we're looking at. That's kind of it in a nutshell. The rest of it is just simply being able to work the problems. So if you are still having trouble solving a system, then that needs to be priority number 1. We got to get the substitution and the elimination methods down. And if you know how to use the calculator, good for you. But again, keep in mind that it is possible that they may make you demonstrate portions of substitution or elimination as the focus of a question that you're answering on a test. Okay, so make sure you know both of those methods. Anyway, there's your Unit 4 review.